Hi, good afternoon, everybody. My name is Esfand, and I'm the Simulation Product Manager Technical. And today we will go through the SolidWorks Flow Simulation HVAC module together. All right, let's start the show and first going through the objectives. What we will do is first going to the HVAC module definition and its capabilities, and we will explore a bit more in detail with doing 3 different case studies to cover all the specs of HVAC module in SolidWorks. The first case study is a 150 watts halogen floodlight. We will learn how we set up a project in flow simulation, and specific highlight in this case study is how we can make goal dependent heat sources, and also how we set the radiation absorption and radiation spectrum. Second study is specifically talking about HVAC or air conditioning system in a hospital room. And the main objectives are viewing the HVAC parameters, make a clear definition of them, how we can activate the HVAC parameters calculation inside a project, and also at the end how we can review the performance of the HVAC system or air conditioning system by looking at the air quality and obtaining the values of comfort criteria. And the third one is the extended, let's say, version of the HVAC, which we have a tracer study in a pollutant dispersion in a street canyon. Well, we are trying to simulate a source of contaminants inside a domain, and we will review the result of distribution for that contaminant substance. All right. Now first go to the definition. Basically, HVAC module is an adding to the flow simulation, which is adding more capabilities to the flow simulation module. So what you can get is the radiation and thermal comfort analysis that will definitely enable all designers and engineers to do HVAC design by efficiently evaluate the gas movement and temperature in a working and live environment. To be more specific and be categorized, the additional capabilities are include advanced radiation model, including absorption of radiation in solid bodies and definition of radiation spectrum, going through the human comfort factors, and enabling the tracer study, which is an analysis of the flow of a certain admixture or tracer in an existing carrier flow. And also, by having this add-in active, you will access a very enriched engineering database where you can see a wide range of building materials, fans, and etc. to run the thermal analysis quickly and efficiently. Okay. Now let's start with the first case study, and we are going to have a closer look. In this case study, we're trying to demonstrate the capability of flow simulation for a heat transfer study convection radiation combination, and we will include the radiation absorption in a let's say semi-transparent solid and radiation spectrum. So we're considering a halogen floodlight with an aluminum housing, or a case as you can see in the picture. That contains a quartz glass front window and also an aluminium internal reflector, that part, and a ceramic lamp holder, and finally it's a lamp, 150 watts linear halogen lamp here. So to have a closer look to the lamp, you can see on the second picture on the right, well, the lamp consists of a quartz glass bulb, here it is, and also a straight line tungsten filament, here is the tungsten filament, and also we have base socket made of molybdenum, and molybdenum pitch pins here, and ceramic base sockets. The lamp is assumed to fill with argon at 2 atmospheric pressure and at temperature of 293 degrees of Kelvin. The lamp operates in a typical indoor condition at the room temperature of 20 centigrade without any forced cooling. So the objective of this simulation is to ensure that the pinch pins and lamp bulb and front glass are not overheated. So the main criteria for such a decision, pinch pins maximum permissible temperature is 350 centigrade and bulb glass is 900 centigrade. So what we do, we set up a study, we go through the advanced radiation parameters, and we will review the result at the end. All right, let's switch to study. All right, as we said, these are the components, and if I do a section view, you can clearly have a look through what we have in this model. So a quick review. Here it is. We have the casing, we have the holder, also we have the reflector, the glass, the cover, and also lamp and a gasket seal. Okay, now let's start with creating a project here. As you know, for flow simulation project creating, we just using a wizard. So by clicking on a wizard, there are a couple of steps that you define in your study and the conditions you would like to put in the project, and when you finish, you will have a new tab in flow simulation. So you give it a name to the project, or if there is any configuration exists, you can simply select to create the project on that configuration. Next step, we suppose to choose a unit system. You can review the detail of this unit system at any time, and simply you can go and change any parameters to the unit as you might like it. So after that, we're coming to a very important step of the project. This is where we're deciding about the analysis type and physical features of the project. So we can simply divide any fluid dynamic or CFD project into internal or external case studies. Internal is a study of the flow inside a closed dome or domain. External is a fluid over some objects. So in this case study, we're talking about external type of fluid, and then on a physical feature, one by one, we will have a review. The first option, if you would like to activate it or deactivate it, is the heat transfer conduction in solid. So basically, everybody knows that heat transfer can be on convection, conduction, and radiation. In this case study, definitely we would like to consider all these three types in our project. So we simply tick on the heat transfer conduction in solids. If you just like to limit yourself to have just heat transfer conduction in solid, tick the second box and make sure there is nothing else will interfere to the project. Next, we have to activate the radiation scheme. If we simply click on radiation, you can see first we have to select the radiation model, which is discrete transfer or the discrete ordinates. We'll be selecting the second one. And environmental pressure temperature is what we have to choose. So we setting as 20 degrees of Celsius or 293 degrees of Kelvin. If there is any solar, let's say, effect you would like to add to your project, here is where you tick in. And now we're reaching to an important, let's say, stage. Absorption in solids, if you like to have this item, click it on, and then also a spectral characteristics. Well, if you click on this one, you simply having the option choosing number of bands for a spectra and also band age and environmental radiation. Since we have only one semi-transparent solid material, the quartz glass, is used in this device, its absorption property are specified as a dependent on a wavelength with an abrupt change in absorption at 2500 nanometer. The UV radiation from tungsten filament is negligible as its operating temperature of 2900 Kelvin, and thus two bands of spectrum with the band's age at 2500 nanometer allows us to simulate the radiation absorption in the glass components of the lab more accurately and efficiently. So number of band 2 because of the band age of operating quartz glass, and we simply getting the environment radiation as a black body spectrum. So we have activated the absorption in solid. We are not considering any solar radiation, and we simply ask for the spectral characteristic for two bands and the wavelength of 2500 nanometer. Just again to repeat, the operation temperature of tungsten, let's say tungsten filament, is 2900 Kelvin. If you are running a transient analysis, this is a place you simply tick on, otherwise it's coming to equilibrium steady state station after the solution finish. Gravitational effect could be activated in any direction as you like. So you can see we are considering a Y component minus 9.81 meter per second square for the gravity, and rotation is for those who are really interested to have a fan inside the domain and look at the fan rotation and sliding mesh or a rotating fluid, where this is not the case in our case study. So these are the major, let's say, decisions we made. There are some further steps remaining, and the first decision is about what we have to use for our fluid. Basically, as we said, we have air around the case, and also inside the, let's say, lamp, we have argon. Therefore, we have to both select air and argon. You can see both of them are being, let's say, marked as a default fluid. So default fluid is air which is everywhere, just one region got argon. So let's tick off the default fluid and make the air as a default. Means anywhere in the project is filled with the air unless we specify a region with argon. You can have a control about your flow characteristic to be laminar and turbulent at here. You can also consider humidity. Well, this is not the case in this case study. Next, we have to make a decision for the solids. So in this case study, we will assume aluminium solid to a predefined or a dominant or preset solid material, unless inside the project we might go and change a couple of let's say components to the other one. But at this step we're saying what is the let's say default solid material. So going next, what we do have is a decision about the default wall radiative surface. So it's now been assumed as a black body wall. However, we would like to define a new model or new surface. Now, by clicking on that one, you're simply accessing the engineering database, the radiative surface predefined material such as absorbent wall, black body wall, non-radiating surface, or white body wall are simply listed here. You either go and review the item properties and look at their specification, or if you like, you can make a new material yourself, like what I've done, and it will go more in detail inside the project. And this item property is basically, it has the reflection of 0.8, specularity coefficient of 0.2, emissivity coefficient of 0.1, solar absorbance of 0.1 for this specific radiant surface. Okay, so either we're using a predefined radiative surface or making a custom made for ourselves, simply selecting that item and clicking OK. You can see that is changed to aluminum polished as a default radiative surface. Means everywhere in the project will use this radiative surface, again unless we are making a definition on any other surfaces. No roughness on the walls, and next we are simply setting the initial conditions. As you can see, the domain is starting at atmospheric pressure, temperature of 20 degrees without any wind direction on X, Y, Z, and also there is no let's say specific consideration in turbulency. We are just simply considering a 0.1% of intensity for turbulence and turbulence length of 0.00761204 meter. Solid parameters, everything is started at 20 degrees. The last step is to set the result resolution and accuracy of our calculation initially. Well, it can be varied from very low accuracy and very fast result from 1 to a very high, let's say, accuracy of level 8. So for this case study, we are simply setting on 4. There are more details about what is getting changed, how we can adjust and locally go through this. So you can access those materials on the other webinars we've done on general flow simulation, and we are not going to spend much more time here. So by clicking finish, you can see the flow simulation project is simply being created, and all the items that we are simply requested are simply listed here. So the flow simulation tree has two major sections, input data and result section. If we expand the input data, you can see there are some definition of computational domain. If you have any subdomain, solid materials, boundary condition, heat sources, and etc. You can simply organize your tree to show more or less. However, you can access all this from your top menu, going to Tools, go to Flow Simulation, and Insert. You can see a lot of input data you can add to your flow simulation, and this is the big list of what you can see here. Okay, the first step when you are trying to do a flow simulation in general is to decide about your computational domain, where the exact calculation are going to happen. So as we said, when we have a look to the model, there is a very good symmetrical sense we can simply predict and observe. Therefore, it is a very wise approach if we can get half of this model simulated and simply telling the software there is a symmetry line or symmetry plane in this model. That can be adjusted by going to your computational domain and edit definition. By default, every project has a computational domain, very simply specifying where are these boundary conditions and calculations are happening. However, you can simply adjust it by drag and drop, or going to the values of X, Y, Z and adjust it yourself. This is based on your, let's say, geometrical dimension and measurement, but you're just putting a value. The main thing is, as you can see, the X plus is being set for the other direction of X, I have signed a symmetry condition. Means although I'm simply considering this box as my domain, that line or that face is representing a symmetrical line. Means there is exactly the same model mirrored on the other side. So the flow simulation project will have one half of it and will reproduce or pattern or mirror the other half later on. So you can have these values set and tell the software that my focus for calculation is inside this box. The rest, which you can see on the hatch lines, are simply getting repeated. That is saving a lot of time for us. Okay. The first step done. Now, as we said, the working fluid is air, except what we have inside the argon, let's say, inside the lamp, which is argon. Therefore, we have to submit or create a fluid subdomain. So, as a default option here, right-click and insert a fluid subdomain. This is exactly what I've done, and if I go edit definition, you can see its detail. All right, hopefully if it's open up, here it is. I have selected a face of the lamp bulb, so you can access any of these components from the tree as well, or simply clicking on the graphical area and say, instead of air as a gas or default one, use argon. You can set an initial condition or flow parameters on this. So inside the lamp there is no velocity and the pressure is 2 atmosphere at 20 centigrade. So the domain is air at atmospheric pressure 20 centigrade. A subdomain of argon is at 2 atmosphere 20 centigrade. This is where, well, the domains are simply starting their position. Okay. Now, in the next step, we would like to specify the heat and radiation condition. The first thing we know, we have heat generation on a tungsten filament. Here is the component, and we would like to, let's say, apply a heat source. Heat source is this option here. Right-click, you can insert a surface source, volume source, or import a data from a model. So simply I've clicked on a surface source and simply edit definition. I've simply selected the component of wire, and then I've asked for a temperature of 2900 Kelvin to be applied there on here. The wire lamp. Okay, so clicking OK, and simply we applied our heat source. Now, next is we have to specify a radiation resource and also making a goal here. One thing I would like to do is to tell the software there is a double precision calculation on the filament heat source, and I would like to use this source and record the data of this source. That can be achieved by setting a goal. A goal can be in a form of global, point, surface, volume, or equation goal. Simply for the heat transfer, as you can see, I have created a surface goal on a lamp wire, and I'm tracing heat transfer rate here. Since I've tell the software record this parameter, now I'm coming to radiation sources. I can select a radiation source and just edit definition. You can see what I have. The face of lamp wire, the two faces, have a diffusive type, and the heat transfer rate or the power here is dependent. Dependent on what? Simply you can see by clicking on dependency bottom, you can say the power that is generated from this filament is dependent on the heat transfer rate recording, 2 minus this 150 divided by 2 minus heat transfer rate. So we make the radiation source to be a diffusive and dependent on heat transfer rate. So every single iteration and calculation is simply tracing the heat transfer rate and making a radiation source as a variable one. Okay, so in this case, we use volume heat resource to define the heat transferred from the filament by the convection. To specify remaining heat power transferred by the radiation, the calculated heat transfer rate of volume source must be subtracted from the heat, from the total heat power. The rest, as what we can, what we have to, let's say, set is the spectrum, and it's black body spectrum at 2900 Kelvin. By clicking OK, you can see a radiation source of diffusive radiation has been added to our calculation tree. All right. Now, as we said, on a general setting, we specify radiative surface as aluminum case. However, there are two more radiative surface which is not an aluminum case. These ones can simply insert it by right click and insert, and if we look at them, the first one is considering the flat lamp wire. It's using white body from the predefined material, so you can review the properties of this white body either to create an edit. You will access the engineering database and then simply look at white body and item properties, what is simply represent. The engineering database also can be accessed from your menu here. So click on that, you will access all the categories of engineering database, such as the information for the fans, heat sinks, radiation spectra, models in predefined, you can see, or even radiative surface. This is the one we have simply, let's say, defined, and you can see the item in categories and item properties here. So what we've done up to this point is simply we insert a radiative surface to the filament as a white body. The rest is still using the default one when we have assigned in our general settings. The other one is radiative surface of the reflector. So if I edit definition this, you can see the glass surfaces has been selected, and this one is simply using a user-defined one, which is aluminum polished. So simply, if you like to create one as a new item here, you click on new, you putting the item variables and simply clicking OK. So we have three types of radiative surface. If I go to general setting, you can see on a wall condition, just a minute here, wall condition, we have aluminum commercial sheet applying everywhere for a default radiative surface, and then we specify two different radiative surface, one on filament, one on reflector, as a two different model. One is aluminum polished and the other is white body. All right, so we have done this step as well, and we are now in the business of saying what are the other solid bodies I do have here in my model. If we like to assign any other solid body, again right click and insert solid material. You can see tungsten solid material has been assigned to the lamp wire, and I have simply accessed it from the user-defined material. You can see here user-defined solid, floodlight, and tungsten with the item properties, as you can see. Density of 19300 and specific heat, which is a table, and you can see it's temperature dependent. So you can do a lot of modification to your items to be temperature dependent on as you import it as a table here. So thermal conductivity, you can see, is still temperature dependent properties. So either you would like to access different solid materials from the user-defined or predefined categories here. Since we have activated radiation, so radiation transparency, we set it as opaque for this material. Now, in the next step and in the next component I would like to show you is about the glass solid material, and I would like to make an absorption in solid activated. So by going here and edit definition, you can see I'm accessing the same database of quartz glass from my engineering database predefined, but this time instead of having an opaque object, I have absorptive, and I'm telling on a different range, less than 2500 nanometer and more than this, what are the absorption rate simply here. So absorptive body is a semi-transparent. It means that absorbs the heat radiation within its volume. This option is available only if the absorption coefficient is specified in solid material definition in the engineering database. And the absorption in solid checkbox is selected under radiation within the wizard. Okay, so because we have these options activated on general setting, if you have a look again on analysis type, you can see on radiation we set absorption in solid activated. That's why we can make a decision here. Alright, so the rest of the study is simply talking about the general thing we're doing in flow simulation by setting up more goals to make a trace of values of temperature of front glass, inside, outside, bulk glass, pinch, and etc. You can see there are some of them are surface goal SG. There are some in volume goal format as it is VG. Okay, so these are the parameters which later on I would like to review and have a double precision and record the value at each iteration step. That's why I'm specifying them as a goal. Since I would like to obtain a very good resolution on inside the lamp, I have set up a local initial mesh refinement here on the bulb and wire. I've set a first level of refinement on solid features. Also, I have activated the refined solid cells on level 3, and also the narrow channel means number of cells across the narrow channel, which is a gap between the filament and quartz glass, which is being set to 7. 7 cells, and number of refinement is 1. So these are more in advanced control about your mesh, and that is guarantee more accuracy of the result. But just simply having a very fine focus or fine element type here will increase your calculation time considerably. Okay, now the setup of the project is finished. We considered heat transfer, convection, and radiation. We activated the radiative surface as one dominant, one local, 2 local. We specified the radiation source, and also we specified the goals and different solid material. Now by clicking run, and when it's finished, you can review a couple of things. The first thing, as we said, was an ultimate goal, is to check if some of these components are not exceeding or overheating their operational temperature. Therefore, The first step we have to do is go and check our goals. So because the temperature is being traced within set of goals here, we can simply go right click and insert. Insert a goal plot means we can select all the goals, which is a trace of temperature at everywhere, to show it, and we have a review. You can see it's their value, average value, mean value, and max value over what we can see. For example, temperature of the front glass is reaching the average value of 405. Temperature of the bulb glass is reaching to 848.2. All of this information is helping us to decide if the design is okay or not. Also, it is showing us these criteria or these goals are being used for making the convergent use in convergency, and also the last iteration, the last two iteration has the delta or the difference, as you can see here. All right, those information also could be exported to an Excel file. Just export here and you will get the information as an Excel file. So all the data in a let's say table view, temperature of solid with the graphs, heat transfer rate, and also the plot row data are simply listed. So you can simply export the convergency, the temperature change, and a summary of what you have achieved here. So it's simply showing us 191 iteration done, temperature of the solid is reached to a converged answer after that much iteration, and heat transfer rate is being also converged. Okay, so this is what we have checked, and we are not seeing any excessive let's say values of temperature on anywhere. So with those conditions, the next thing I would like to show you, and probably you have experienced it before, is the ability of making different cut plots. You simply right click, insert, and you can specify your cut plot to cut your model in any direction you like. So I've chose right plane to show contours of temperature. You can have multiple items by saying contours of temperature, vectors of velocity, and etc. and etc. So you can make any complication as you might like to create. So simply showing this, I can highlight the temperature distribution inside and outside the floodlight domain, where the heat source over the glass bulb and how it's affecting its let's say surrounding, and what is the actual temperature outside the domain. Okay, so this is simply introducing the first capabilities you will get in HVAC module. All right, now we are ready to move to the second case study, which we're talking about HVAC module in hospital. So let's save all and let's come off. Okay. Now the second case study. We're talking about air conditioning in a hospital room. So the purpose of this study is to predict the performance of a building ventilation system and to estimate air quality and general thermal sensation by calculating the comfort criteria. Okay, here we are. We consider a hospital isolation room and estimate the ventilation system effectiveness with respect to contaminant removal and thermal satisfaction of the people in the room. A typical patient room includes standard feature as a patient bed, you can see it here, and also exhaust in different locations, lighting equipment, and etc., as you can see in the feature. The overhead ventilation system contains an overhead ceiling supply diffuser where we have this entry as the location you can see, and we have the ceiling and the washroom exhaust, so two outlet, forced air removal here and washroom exhaust vent grill. The source of the contaminant is just the patient breath. So we simply assuming the contaminant is the outflow from the patient's mouth, and we would like to see its let's say distribution over the domain and see how does it getting let's say spread. Now have a closer look to the boundary condition. You can see the initial condition of the room temperature is 19.5. It's full of air, pure air, so the mass fraction of air is 1, and mass fraction of the expired air is 0. We have different heat sources, such as TV set with a heat transfer rate of 50 watts, hospital equipment of 50 watts, a caregiver with a heat transfer rate of 144 watts, ceiling lights with 120 watts here. The inflow is a forced inlet fresh air with a volume rate of 4.8 meter cube per minute. Also, we have the patient breath, which is a flow rate of 12 liter per minute. Well, the mass fraction of fresh air at this source is 0. The mass fraction of let's say expired air is 1, and also the patient generating a heat transfer of 81 watts. The outflow, we have the first exhaust vent grill, which environmental pressure at 19.5 centigrade, and also we have the forced air removal with the volume flow rate of 2.6 meter cube per minute. So different source of heat, inflow and outflow, and there are two sources. Well, we have different let's say fluid, air fresh, which is all filled inside the domain initially, and there is an expired air which is coming from the patient side. What we're trying to do is simply set up this project and then look at the ventilation system effectiveness. There are some parameters that we would like to trace. The parameters with respect to contaminant removal include contaminant removal effectiveness, or CRE, local air quality index, which is LAQI, and there are some parameters with the thermal satisfaction of the people inside the room, such as PMV, predicted mean vote, air diffusion performance index, APDI, and predicted percent dissatisfied, which is PPD. Alright, having a closer look to the definition, the human comfort parameters. First is PMV, is an index that predicts the mean value of votes of a large group of persons on a 7-point thermal sensation scale. So it's very cold, it's ranked -3, it's very hot, ranked +3, anything between, the perfect one is 0. PPD, or predicted percentage dissatisfied, is an index that establishes a quantitative prediction of percentage of thermally dissatisfied people determined from PMV. And operative temperature is the uniform temperature of an imaginary black enclosure which an occupant would exchange the same amount of heat by radiation plus convection as the actual non-uniform environment. Draft temperature is the difference in a temperature between the patient and occupied zone and the control condition. Draft temperature is valid for fluid area. And the last parameter for human comfort is the air diffusion performance index, is the percentage of the space in which the air speed is less than 0.35 meter per second and the draft temperature falls between -1.7 centigrade and 1.1. So these are the main parameters for the designers of HVAC to trace. These are called comfort parameters. However, we have the second set of let's say, parameters when we have a contaminant resource in our domain, and they are contaminant removal effectiveness, or CRE. This is providing an information on the effectiveness of ventilation system in removing contaminant air from the whole space. For a perfect mixing system, CRE is 1. Values about 1 are good values. Values about less than 1 is very poor. And the second factor is local air quality index, LAQI. This is an index which is providing information about the effectiveness of ventilation system in removing contaminant air from a local point. All right, so with that definition, it's now the correct time to go and have a look to our project. So this project, as you can see, is being set up, and it's trying to converge different goals. You can see it is still on the progress of convergence, and it's trying to finish the solution. However, what I would like to do is simply stop, save the result up to this point, whatever it is, and then going through the step of project creation. Okay, so let's give it a time to simply finish and save our results. Okay, yes, save, and then we will back to the project. All right, while it's saving, let's have a quick look about the regions and domain as we simply described it before. Here is the caregiver, here is the patient bed, and you can see we have different area in the model. That's the room. We have the bed, caregiver, patient, and the fluid domain, where this is indicating we're talking about an internal fluid. In a caregiver, we can see there are some assembly, and these features are simply being added as a sub-assembly to the main assembly on the project. So the solver is now finishing, and sorry, it's about a bit slow. And yes, solver finished, and we are loading the results. Okay, now it is okay to close this. Perfect. All right. Okay, sorry, retry. Good. Now we will just get back. Again, the procedure is starting with a wizard. This time what we're supposed to do is simply go quickly to our project, making a decision about the unit. This time we're talking about internal flow. Internal flow means we have a closed enclosure. What is very important when you're doing this type of let's say flow analysis, you have to close your domain with all leads and make a cavity let's say active on your project. This information is again on our general webinar about the flow simulation, and you can find more details about it. Okay, so what we would like to do is simply activate the gravity here on a Y direction, and then going to have the selection about our gases. First, air from the list of the gas, and also we can add or create a new material at this stage. So a new material we can add. You see, gas, predefined, user-defined. I'm in the actual position of creating a new material. That's what I've done, and it's called expired air. Expired air has the properties as you can see here. Dynamic viscosity, specific heat, and thermal conductivities are all temperature dependent, and that is being created before here in the project. What I have to do is simply in the gases, not from the predefined, from user defined. I would like to add it. Okay, and simply I have defined my two substances of fluid inside the project. Okay, I'm simply removing the tick. Go next. This time wall condition, I'm considering adiabatic wall. There is no heat transfer to the surrounding and the wall has zero roughness. And then from here we would like to go to initial condition. You can see the initial condition is considering 20 degrees of temperature, atmospheric pressure, velocities of 0, and also here we have no mass fraction in the contaminant air. Sorry about this. Next is what I have, resolution 3 and finish. When I'm doing this, I have created my default project. Anytime if you have created your project and you would like to review the result of this, the parameters, right click on the input data, go to general setting and have a look. You can see internal, gravity active, on analysis type. In the fluid you have air gas and expired gas. In wall condition, adiabatic wall and no roughness. Initial condition, we have atmospheric pressure 19.5 centigrade, zero velocity, and also we have concentration. Initially we have 100% fresh air, 0% expired air. That is where our domain is simply start its condition. Okay. Now what we have to do is simply to specify the boundary condition as airflow in, airflow out. You can see boundary conditions are simply listed here. Insert a boundary condition. You will make your selection on the face. Inlet volume flow 0.08 meter cube per second. You can set the thermodynamical let's say parameters and also substance of mass concentration. 100% air fresh is coming to this resource at this volume flow rate and temperature and pressure. Similarly, the outlet flow, we have that face, outlet volume flow rate, and this is the volume flow rate as been defined in the project description. Third is environmental pressure on this exhaust gas grill at environmental pressure 19.5, mass concentration, it's 100% air fresh going out. Next is inlet volume flow, and this is exactly where we're trying to set the contaminant air or expired air. If you look at the patient, there is a surface which is representing patient mouth, and I've select this inlet volume flow. The value is 0002 meter cube per second, and it is simply having 100% expired air coming out. Okay, so we have set all the fluid or flow boundary condition by inlet and outlet into the room, in from the patient, outlet, and environmental pressure at different stage. Okay, now the next step is simply to make the heat resource or specify the heat resource. The procedure is look like again the same thing as what we done. Insert a surface source or a volume source. You selecting the patient as a whole body. Always when you selecting something from your tree like a patient, you can list all component face by clicking on that one, and just in case if you need to delete any face, you can right click and delete. Next stage is simply to apply a heat transfer rate of 81 watts. So one by one, the patient 81 caregiver 144, ceiling light 120, TV set 50 watts, hospital equipment 50 watts. We have one by one selected the heat source on these surfaces. Okay, now this question is, up to this point, everything is look like exactly the same thing as we have in flow simulation. How we can activate the control options in HVAC module to get all these human factors, let's say parameters, comfort parameters. This can be simply activated by right-click on your input data and look at your calculation control option. You can see for finishing condition, I've asked all my goals, which is mean radiant temperature, operative temperature, velocity, and volume fraction of the expired air to be converged. And then for the refinement, I have a local initial mesh. For solving, this is exactly where we are talking. Additional parameters. If you have appropriate licensing, then you can access those two parameters. Calculate local mean average LMA, calculate comfort parameters. This is exactly the place you can activate the calculation of HVAC parameters. Okay, so simply we are activating the HVAC parameters to be calculated, and what we need is again set of goals, any refinement on the mesh, and then solve and look at the results. Okay, before we looking at the results in the figures form or cut plot, what I would like to mention here is how we can get the CRE value. All right, if we right click on results and then look at the summary here, you can see some very useful information about the project, and then the CRE of air is 1, CRE of expired air is 1.3. This is not 100% let's say converged answer, but it's very close to the final answer because I've stopped the let's say the calculation within when I was presenting, just to show you how the calculation are simply getting the graph of the convergence. Now, these are the information and these are the CRE value. Either if this is a target value for your CRE, you can confirm your project or you can reject it. Now, the other thing I would like to show you before we doing anything else is the reference parameters for the HVAC module. If we go to Tools, Flow Simulation, and on Result, you can see the default reference parameters listed here. Fluid temperature and comfort parameters. Metabolic rate of the people inside the room, this is what you can assign, 100. Second is external work, 0 watts. The other is thermal resistance of the clothing, it's 0.11 Kelvin meter square per watt, and also relative humidity of 55%. You can have more control with assigning a pressure and also velocity and distribution. So in order to get more realistic data for your calculation, you can modify the default reference parameters here on your project. Okay, that will include the metabolic rate, external work, thermal resistance of clothing, and relative humidity. Okay, so the relative humidity of 55% is typical for indoor condition, and we are happy with that. values. The other values are simply can be found from any resource, any table, but mostly the default values are very reliable. All right, now we would like to look at our goal plots and volume parameters. The first thing, if you like to have a goal plot, insert and simply edit definition and look at the parameters. Okay, so it's while it's going to calculate all these, here it is. You can see the PMV, PPD, draft temperature, LAQI of the air, LAQ of the expired air, all over the domain, minimum, maximum, and average. Again, you have the option to export this to Excel. The other thing we would like to have a look is again our goal plots, looking at their value and telling us how we accurately convert our answer. These are the acceptable delta, and we are having a very fine criteria to convert. So I can rely on my answer here. Okay, and again, any goal plot, any cut plot can be simply activated by going to your edit definition, contour of pressure, or any values of human factors such as PMV, and show it and look it here. So it's looking a bit of contamination around the patient mouth, and if we're going down, we can absorb more and more here in our graph. Alrighty guys, so that is what we can do. Also, you can do a lot more by creating ISO surfaces, and let me hide this. Let's create an ISO surface that is showing the PM value. The first value is 0, the other is 0.25, and you can see the range. If I say show, it is simply highlighting the region with those values of PMV, and you can make a decision about how the comfort parameters are look like, how the contaminants are being removed, and if it is a very effective system in your design. All right, now we are just running short out of the time, and I would like to go to the last case study. Well, the last case study is talking about pollutant dispersion in the street canyon. Basically, we have a couple of buildings, and there is a traffic between the buildings, and this is the source of a NOx, let's say, contaminant fluid here. We have the air winds through this whole domain. We simply evaluating the air wind to be varied in a varied by the height. Well, the wind speed at the height of H is VR, which is a known speed at the reference height, could be 0, could be 100 or anything else, times the ratio of H over HR and an exponent, which is atmospheric stability. That is range between 0.1 and 0.6. That is an engineering approach. Therefore, we define this project to have a wind flowing over those buildings in a Z direction, varied with Y happening with this formula. Turbulent, let's say, turbulence energy of 0.59 joule per kilogram, and also turbulence dissipation to again be dependent on Y value. What we're trying to do, while we have a NOx as a source of contaminant coming from that surface with the mass flow rate, as you can see, how the distribution of this is look like. All right, let's go to the case study. Here it is. You can again have a look. I'm going through the wizard. It's an external flow. Have a quick look to general setting. We have external flow. We have a time dependent. So it's looking at the variation of time. It might not be a convert or final equilibrium sort of answer for this project. Fluid is air as a gas. Wall condition, adiabatic, no roughness. Initial condition. This is where I would like to show the next trick. It is atmospheric pressure and 20 centigrade. As we said, the wind in a Z direction is dependent on the high. So by selecting that one, click on dependency, you can put your formula for your initial condition here. So I've defined the wind speed over this domain or over those objects to be varied with the Y value. Also, that is true for turbulency dissipation. It is dependent on a Y value or the height. So even in your initial condition, you can define a formula. Okay. So as you can see, I have made a decision to have this as my computational domain, and there is symmetry on left and right. So look at edit definition. I have x plus and x minus as a symmetry condition. Also, I have set up the goals. With that initial condition, as I showed you before, wind speed on Z direction, I'm running my study, and now it is the time to specify the source of pollutant, which is a NOx gas. Tracer study can be inserted to your simulation by going to Tools, Flow Simulation, Insert, and Tracer Study, as you can see here. That is exactly what I've done, and that's it. Okay. Now you can set up a study as a new study, or going through a wizard, Tracer Study, and say what sort of material I would like to have as a contaminant resource. You can see there is a list of predefined, and if you are like, you can create one yourself. Create and edit. Again, I'm going to my engineering database, the item, tower block, and NOx is what I've created with the properties as you can see here. This is the resource and properties of my contaminant as a NOx. Next, I have to say this needs to be added, add a tracer study, and go next. It could be a time dependent, and for how much, what sort of time frame, and saving the result with what scheme. Clicking on next, and the mass fraction is what we have to assign here. Well, we are assigning the values as we agreed, 0.8 something for the value, and simply let me assign. Where is it? Here it is. Alright, so the mass fraction is 0. Okay, and then next we are simply selecting the source of contaminant from this face, and mass fraction as 8.6515 E minus 5. Okay, so next, and then you run this. I've already done that one, so you can see my phase 1 having the mass flow of this contaminant NOx to be simply injected, and then I've run the project. The first thing we would like to show is the flow trajectories. This is how the flow is simply getting distributed, and then I can show the ISO surfaces for any parameters as I might like it. So let's look at the tracer study, add parameters and custom. Hang on a minute, it's just been somewhere here. Okay, hang on. All right, so let's go and create the surface, ISO surface for the tracer study. Okay, add parameters. Heat, turbulence, custom, position, relative, okay. There it's gone. Sorry guys, I'm trying to find this one. Appearance. That is a bit okay. Alright, so let's run our tracer study again. Might not be a valid run. I just need to run the tracer study. That's why we are not having those values active. So I'm running this tracer study. After you finish the whole project, you run the tracer study and make an update of calculation everything, and then when you coming to your ISO surface and insert, this time you can see the tracer mass fraction as the value. You can see this value is simply happening here. So you can simply have a look to the concentration of the contaminant inside your domain. You can have more and more items by making cut plots, insert, and also here making your first cut plot on let's say right plane, and then tracer mass fraction, and show this, and also making another cut plot active here, and then simply this time I'm looking at top plane, tracer mass fraction of NOx, and clicking OK. So simply hiding the ISO surfaces, hide, and I can look at the mass concentration of NOx inside the domain. So that will help us to trace the contaminant resource, its distribution, and if we are simply trying to let's say design anything to remove that, that is almost welcome. Alrighty guys, so this is bringing us to our conclusion. So it is quite intense webinar it was for today. If you have more technical, please contact me, esfandyar.kouhi at intercad.com.au. I'm a product performance consulting manager and working with John Belsham, which is the simulation product manager. For more commercial discussions, please have contact with John, and we can organize any let's say specified demos or any case studies as you might like it. Thank you all for attending, and hope to see you again later on the following webinars.